Okay, first I want to explain what I will be doing today. Today we will go over the introduction to ANSYS Fluent tutorial 1. It's about the Laminar. As you know, you have two assignments, tutorial 1 and tutorial 2. It starts as Laminar, then goes on to turbulent. And each student is required to write a report about this. It's a take-home individual task, and we will expect results from each one of you. In terms of the report, I will discuss this and maybe send you guys a format of what is required. So we will wait for this. I want to ask, did any one of you guys manage to install ANSYS? Because I sent the instructions. The instructions has been posted on Blackboard, and I hope you guys can really try to download it as soon as possible, because each one of you needs to conduct the simulation. Okay, that's good, Sultan. So I will do the entire tutorial, and this session is being recorded, and after that you can follow it step by step to better learn. So let's first study the problem that we have. We have a pipe. It's a cylindrical pipe with flow going inside, and it has specific diameter and specific length. But what happens is that in simulations, we always aim to make things more simpler and reduce the size as much as possible. So in this example, what we will do is that we will take only a cross section of this pipe. This pipe is 3D, so if we take a cross section from here, imagine that we cut this longitudinally, so we will have a 2D surface, right? So this is not enough. We want to make the problem more simplified. So we assume that it is, since it's cylindrical, it's axis symmetric. It's symmetric around a specific axis. So we assume that this axis is at the center, and we divide our 2D surface into half. So in the end, we will have only this rectangle. I'm not sure if you can guys imagine, but when we do the simulation, it will be more clear, hopefully. So now let me open ANSYS to show you. I already tried the simulation and it works, so this time it should also go smooth. So first of all, in terms of the geometry, we will do right click, and there's a new discovery geometry, space claim, and designer modular. There are three softwares. And as you know, this tutorial is old, and it was first using the designer modular. This is called, wait, let me show you guys. Yeah, this it was very old, and it's doesn't exist, I think, anymore. Let me check. Yeah, it's still there, but it's very old, and nobody uses it, and it's very slow also. So we will use Space Claim. In my opinion, Space Claim is the best CAD software currently existing. It's very, very strong, and you can do anything with it. It's much better than Creo, much better than CATIA, much better than SolidWorks also. So let's open it. And while we open, let's see what is required of us. It says here that we want to create a 2D shape. Sorry, I mean, it says that the diameter of this cylindrical is 0.2, and the length is 8 meters. Since we divided it by half, we will have diameter of 0.1 and the length of 8 meters. And the fluid is not water, it's oil. It has density of 900 and a kinematic viscosity. And in terms of this is the kinematic viscosity, so the simulation will require the dynamic viscosity, and we need to output this. This is the input velocity, and it will output around this Reynolds number. Of course, we know this Reynolds number is equal to rho Vd over mu, which is equal to, let's calculate it. The density is 900. The velocity is 0.6366. Rho Vd. This d is 0.2 over mu. Let's check. Well, so we have 900 the density. Sorry, 900 rho density V. It was I think 6336, right? 6366. The D diameter was 0.2 in meters. This was 0.45. This is the Reynolds number we have, 253.4. Yeah, almost correct. And we know that for Reynolds number, this is experiment number 7, which you guys still didn't do. But we will discover in that experiment that Reynolds number below 2000 is considered laminar. So this tutorial is purely laminar simulation. Going back to the software, we first open it. We click this button here. Then we will go to select, and we want our geometry to be in the X and Y axis. So once we click those, we go to create a plane. And then we will go to sketch and click start to do the rectangle. So the rectangle, we know that its length is 8 meters. So this units here is millimeters, so it will be 8,000. And the height is 100. As I mentioned, it was 0.2 meters, but since we take only the half, it will be 100. Click enter. After I click enter, this is the geometry I have. I will click this return to 3D model. Zoom extents. This is what we have. This is the 2D sketch plane that we want. So this is it. This is the part 1. We close it. And as you can see, ANSYS it goes step by step. We have geometry, meshing, setup, solution, result. So we will follow it as following. Here we need to change the domain from 3D to 2D. So we press it here. And then we go to the mesh and we double click it. So this was part number 1. We finished this. We created the geometry. Using designer modular will be much more complicated. So we got that. We finished it. So next up is meshing. We want to mesh. What's basically mesh is like solving a big problem in small sizes. We have a surface and we will separate it into elements. And we want here to have 3,000 elements for this entire sketch. How we will do that is that we will divide the length by 100 and the axial direction in the axial direction, and 30 elements in the radial direction. How we will do this, I will show you guys now. Here we see it's imported, and we see here its plane is XY, so it's 2D, everything correct. If this comes out as 3D, that means you did something wrong. Go back and double check. So let's first create the mesh. Here we see we have 1, 2, 3. Let's go to statistics. We have here 20 elements. 20 elements is not enough. We need it to be 3000. So go click face meshing, click this face, and then go here, apply, and then let's go generate. It will be still the same. Then we will do sizing, the insert sizing. Here he mentioned that he wants 3,000 elements by dividing 100 ms in the x direction. So we will click this edge here and click this edge and this edge, two edges, apply. So here we see geometry is two edges, and the type that we want is number of divisions. Number of divisions, as he mentioned, 100. As you can see, we will divide this length by 100. If we click generate, we see here we have 100 structured elements. And then he mentions that we want 30 elements in the radial direction. So let's go insert again, sizing, and we need to click this edge, this, and this one. Apply, then number of divisions, 30, enter, generate the mesh. We have done this. So he said that geometry will be meshed with 3,000 elements. Let's check if this is true. We go to elements, we see it's not 100%. Why? Because like when we did the sizing, there's a capture capital, we have to apply no, and make it hard. Capture capital no. Let's check how. Should work now. Yes, here we have 3,000 elements. What happened? Why we got different number? Because ANSYS has its own code, and sometimes he says that he knows better, and he will decide what's the best. So that's why he modifies it. But of course, ANSYS is smart. But for our case, we will choose the specific values. So after we did the mesh, we confirmed we have 3,000 elements. It's correct. Now, ANSYS is smart enough to understand what are you doing. So we need to create names. As we can see here, we need to create the names called name selections. Left inlet, pipe wall, center line, outlet. We need to define those in the mesh window. So right click on this, create name selection. This was pipe wall, correct? Yeah, pipe one. The left side was the inlet. Did I press it correctly? Let me check. Yeah, inlet. This is outlet. Okay. The down one was center line. And the outmost right was the outlet. Let's zoom in so I can click it. Click this one, base edge, different section, outlet. So now we are done. Let's go back, double check. Outlet defined, center line, inlet, and pipe one. We followed this, and now it's correct. So what we will do, before closing this mesh, we have to click update. The mesh translation to Fluent was successful. Then close this. Why does this happen? Because ANSYS is a collection of different softwares, and those softwares don't know how to communicate with each other. ANSYS just combines them all together. So this is ANSYS keeps buying those softwares. So that's why ANSYS has so many things, and they are very slow because they don't know, they are not fully coupled, not integrated together. Double click the setup and do double precision. And here we see that parallel local machine processes we have. Each computer is different. Let's go to my task manager. I am using the university laptop. We go to CPU, we will see that we have 4 cores and 8 logical processors. So we can put here any number between 1 and 8. I will choose 4 as 4 number. Click start. It's slow, but to know that what's going on, we see that at the bottom left corner we have starting fluent, so it's working. We have to just be patient. Now we are at step 4, the setup for the physics. Here mentions double precision and then opening. Here it said like we want to check what we open. This is a notification for a new mesh method in ANSYS. As you can see, I am using the 2026 R1 student version, and I hope you guys download it. So now go check mesh size. We see that we have 3,000 cells, 6,000 faces, partitions 1, nodes 3, 1, 3, 1, exactly as the tutorial. Then we will do here 2D plane axis symmetric. It's symmetric around the central axis. Then we go to modules. Here we see the viscosity is SSTK omega, which is for turbulence. And we will switch it to laminar because we have 250 Rayleigh number. It's considered laminar. Then we go double click the materials. We go to air, double click create audit, and let's see what we have. I remember we have oil. Then where is the properties? Yeah, here. Rename the air to oil. Of course, the tutorial is very detailed, so follow it, guys. Density 900 and viscosity, dynamic viscosity is 0.45. 900, 0.45. Overwrite the air material. And then we will go to the boundary conditions. We have a center line. The center line is considered what? Considered an axis. The axis that the simulation will rotate on. And the inlet, we will have components, and we will have axial velocity and without radial. Remember 0.6366. 0.6366, and the radial velocity is 0. The inlet, this is for the inlet. The outlet is pressure outlet. Center line is axis. Pipe wall remains. Apply close. I see outlet is pressure outlet. Pipe wall is wall, and we just define that the center line is axis. What does wall mean? It means that it will apply the no-slip condition. Yeah, the no-slip condition. Moving on, we go to reference values. Reference values are important if you extract results from ANSYS. But if you do not do that, it's fine. I would choose compute from inlet. We'll have this area, you can change it as you want. We have density 900, correct. Length, yeah, this is just a regular thing to do. Then we go to methods. We will keep the things currently, but we have to this proceed time method. We have to make it off, and just like that. Then we go to monitors residuals. Residuals basically means error percentage. It's the error that we will get because this is simulation. Continuity is mass. So if 1 kilogram it goes inside, it will not come 1 kilogram. It will come 0.9 kilograms. So this saying that resolve for the simulation, keep resolving. So it solves again. It becomes 1 kilogram inlet, 0.99 outlet. Solves again. then the output will be 999, and then it will keep solving till we get the error of 1e negative 6. So it will be 0.69. Okay, finish this. Then we go to initialization, standard initialization. Initialization means deleting the current results and initializing the simulation. If you run it and then want to change something, you have to initialize to remove the current run. So should be everything correct. We following the simulation here, criteria A all to E1 and E6, give it 2 minutes, standard initialization, and then we will put the number of iterations to solve 1000, and it will keep solving till it reaches the error specified here by the continuity. Here you see one, when it reaches 1e minus x, solution is converged and it stops. So let's see what will happen when we run 1000 number of iterations. Let's do check case. So just check your mesh just in case. Perform mesh, checking mesh, done. Let's run it. Yeah, Bismillah. We'll see what will happen. Hopefully it goes smooth. If something is wrong, of course, we will fix it. Let me check. Let me check this something here. Of course, the speed will depend on your commuter, but it should be overall fast. It's only slow because ANSYS is slow, not like it's not always the PC's fault, just because it's communicates very slowly. Now starting, here's the residuals error percentage converged. We see that it's managed to converge at 41 iterations, and it reaches the residual E negative 7 for the continuity. Continuity means mass. So this is correct. In the tutorial, it mentions that 95, but of course this is old, and the main thing is the results. We will see the results if they are accurate or not. So then we will save it, and then we will go to extracting results. As soon as this stops, we go. In terms of the results, I will share with you guys what we want exactly, because I cannot say something now because we have many sections, and I need to talk to the TAs. I need to talk with them so we can all agree on a specific template that guys can submit. That all the TAs agree on, and will grade it equally. In my opinion, I care mostly about quantitative results rather than qualitative. So we'll focus on numbers, but I will show you also how to extract the velocity vectors. Equation complete, then save the project. So the solution is basically the run that we just did. It is the setup, but if you want to check your solution, you don't go to setup, you go to this solution. So I just did the update for it, and we'll see. Really, the ANSYS is a great software. It has many advantages, and I recommend that you guys take this very, very seriously to learn it, because this skill will follow you forever, really. Simulation nowadays is becoming very, very popular, and you guys really should try to utilize it. It's much better than experimentation because it's very cost efficient, and you can do it basically anywhere. But experimentation, you need very expensive machines, so you will not find that any place. I did update, and then we'll go to results to visualize it and also take qualitative and quantitative results. Let's start. Go view to the z-axis, and then let's create a contour. Here, first of all, velocity vectors. Here it is, vector. We call it velocity vectors. It's at the all domains, location, periodic one. Sample size 0.1. Vertex. Wait, sorry. Instead, specified the name as velocity vectors, all domain options, and fish set periodic one. Click the apply button. The resulting velocity vectors, the arrows are too big. This is what happened. You can see here. The arrows are very, very big. So select the periodic one. The arrow sizes may be can be made small as follows. Simple size. Wait, let me check here. Remember this. Then we go back to the velocity vectors. Go to symbol. Yeah, 0.1. Here are the results. Let's check out the very end. And here we see that the maximum is 1.272. So this agrees with the results 261, 272, almost same. Now we'll extract more results. Next, we want to see the velocity magnitude contours for the velocity. Let's create this velocity magnitude contours. Let's hide this one and apply this for the velocity magnitude. We can see that when the velocity enters, it's still not fully developed. So here we see that due to the non-slip condition, we will have this boundary layer, and this boundary layer keeps forming, keeps developing until it is fully developed, and then the simulation, the results will be steady. You see that we're going, it's not changing. It will become steady after a point. And what is this point? You guys need to find this exact number, and now I will extract it. Here we see we can do animation. That's fine. We will not do this in the report anyway. So now we want results. Here it mentions many things, but we don't need to do exactly what they are doing. We can do it differently. We'll go to location, and then we'll create a line. And this line, we will call it call it center line, and it will go from 0 to 8. Center line, and it's going from 0 to 8, and we will have 100 samples. As you can see here is the line that we created. It's in dotted form. And then we will do create chart, what we will name it, axial pressure variation. Axial pressure variation. Data series, it will be the center line. The x-axis will be what? X, and the y will be pressure. Let's apply. We see it will go from 2000 to 0. Let's check with the results. We see here it's 2000 to 0 along the channel. So this is correct, but of course we will need to find the maximum value. So how we'll do this? We'll do export. Here's the location. This is the axial pressure variation. Let us find it. It's an FF1 fluent or no? Where did it mesh? Export. It's an fluid lab files, user files. Fluid lab files, user files. Yeah. Let's check. Edit in Notepad. We see that the maximum value was like this, 2054. And here we see that it's 2049. So you will need to calculate the error percentage between them. And this is what we want in the report. We want those value and the error percentage compared to the, here we have theoretical. We want to compare the theoretical with this numerical. Find the error between this one, 1800 to this result. Of course, we see that we have 11% error. Of course, this error can be mitigated using finer mesh. We have only 3000 elements. Maybe if we can do 6000 elements, the result will be much better. So going back, we want to create a new line. Of course, you have to include this in the report as well. Take screenshots for it. We expect to see it in the report. So next up, we want to do a new line. It's from 8 across the end, across the height. So let's do location line. What is it called? Pipe outlet. Pipe outlet. It goes from 8 to 8 to from 0 to 0.1, and it's 100 samples. And go to chart. So we'll create a chart called outlet velocity profile. Outlet velocity profile. Data series, it will be the pipe outlet. The x-axis will be the velocity, and the y-axis will be the y. Let me check. Velocity and radial distance y. Okay, let's apply. Here's the values that we have. Let's do the same to find the maximum value. Outlet velocity. We see that at the last we will have, sorry, the velocity is at this value, so it will be 1.27. 1.27, and here we see that the maximum velocity along the center line is around 1.27. The theoretical value is 1.27 also. Please compare your value with the theoretical value obtained in the tutorial by the equation they specified. So here we see that also we can use this one 5.4. We can by this equation we can you can solve it in Excel and output the results. Combine the results between the ANSYS and theoretical, and we will see very strong correlation. This one figure is required. Then lastly, we want to see the centerline velocity. We will create a chart called centerline, and we'll do it for the centerline. So let's go here, centerline velocity. For the centerline, the x-axis will be what? X, and this one will be velocity. Yeah, this will be 1.27 also. Yeah, just showing it. Why we want to see this? We want to see that when the results will converge. So when the bunch will, he says that we see that the results converge at 4.525. So let's do this. We want to see that when the results will stabilize. So here we see that it starts from 6 e minus 1, then goes to 1. Here 1.1, 1.2, 1.25, 24. You see the difference is very small. And here we see that the results almost converge here, 1.27. It starts at around this value, x is equal to 4.44. So we will consider, see here 1.27 stays the same, 1.271. So the very start will be our convergence. Here, let's see. It's around 5 meters. Here he found the results to converge at 1.27. It's 4.5. So at 1.27 start from here at 4.44. So we are almost the same. Please write this down and calculate the error between yours and this value. Lastly, I think this is the last thing. We want to find the skin friction coefficient. Skin friction coefficient, we'll extract it from the results. So let's, now I think we finished here. We go back to the solution. Let's first save it just in case. And click the solution. We have to go back to here to extract this very last value, the skin friction coefficient. Notice how I clicked on the solution, not the setup. Please do this. If you click on the setup, it will remove your already existing results. We will wait for it to done. Load up, finish. Okay. Go to plots and then right click XY plot, and then we'll do a new one. We'll call this skin friction coefficient. It will show the wall fluxes, which exactly the skin friction coefficient at the at the wall, right? At the pipe one. Let's show save and plot. Here it does with us. We see that it goes down and then converges. We want to know the value it converges at. So we do write to file, and here it saves it in this location. Skin friction coefficient. It saves it in different location. It was dp0 ff1 fluent. Here it is. Edit in notepad. We'll see the value at the end. At 8, it is 0.062 at 8 meters. So we need to find the result at 8 meters. 0.0627, 0627 exactly. When we make this 5 because it's next to our 6 the 6 becomes 7 because next to the 5. So we will get accurate solution. Here the results is not in order, but yeah, it's you should go at the 8, which is the length of the pipe. So this is the last thing. You need to find that the simulation, and then we will have to compare it with the theoretical. Don't compare with his simulation results. Compare with the theoretical values. Write this equation in the report, calculate it, and then compare with the results. Here we see that we got a value. When he got error percentage value of 0.2%. So how many numbers we will have to include? Here we include one number for skin friction, two numbers, 1, 2 for the when it does fully converge, and three numbers for the maximum velocity. Of course, we include this figure and this figure. And so here now, did I reach 3 or 4 numbers? Wait, 1, 2, 3, yes. The 3, and I think 4 is the pressure, right? 4, yeah. We have 4 numbers and 2 figures. I mean, sorry, 3. 1, 2, 3, and 4. Yeah, so 4 numbers and 4 figures. You guys need to do this. And this is very important to do, this comparison of outlet velocity profile with theory. This is research level, and you need to do this to learn. So this is very important. Try to replicate this. So this is the end. After this is finished, how we can extract this, we can go to save picture for this, use Windows resolution, white background, preview. Here are the results. And here we click view, here we click save, so you can save it on your computer. This is the end of the session. You see the simulation is very easy, and I think you guys can do it with no problems. And if you face anything, you can ask.